Okay, we're now live on the Hangouts on the Air for our structural modeling video conference for May, this first Saturday of May, when we get together and discuss activities associated with structural modeling, interpretive structural modeling, and other areas of interpretation of human structural activities, language, models, complexity. How do we basically address these things? Kind of as an introduction and a bit of a historical note to give it some context, we have over the last year created a series of computer-based models that explore certain natural language relationships and how those natural language relationships are mapped to mathematics, and it allows us to have the tools available to mathematics and the tools available to natural language to integrate those in a way that we can effectively address the solution to complex system problems. So we started with Peter joined in. How are you doing? Good to see you.
Thank you.
Well, I'm just doing a bit of a historical notes here to provide some context for our video conference today. And I'm not familiar with you, so if you could give us a bit of an introduction, and I think everybody else will introduce themselves, we'll get to know each other a little better.
Sure. Well, yes, I can do that. Is that what you'd like me to do right now?
That would be great. Yes, please.
Okay, my name is Peter Tuddenham. I founded an organization called the College of Exploration 21 years ago, but I'm here primarily as VP of Systems Education for the International Society for System Sciences. And I'm also a member of INCOSE and the System Science Working Group. And I'm developing ideas and actions around sort of a next generation systems literacy. And I'll be hopefully running a workshop in Edinburgh at INCOSE on that. And I've been familiar with John Warfield's work since 1983-84. I was introduced to it by Bill Reckmeyer, and then met John Warfield and Aleko at George Mason Universities in the late 80s. And so I'm very interested in the whole evolution development of interpretive structural modeling and what you're doing. So that's a brief intro.
Well, thank you, Peter. Now that you've said those things, it kind of jogged my memory a little bit, so I made some connections with that. That's good. That's very interesting. My name is Joseph Simpson. I've been working in this interested in working in this particular area for about 25 or 30 years. Started with just a brief introduction to Warfield's work in the 80s, and then in the 90s and 2000s, when I was doing some work for the Department of Energy, I ran into the work that Warfield had done at Battelle and started seeing how that could be applied. Discovered a number of barriers that seemed to be, at that particular point in time, were insurmountable because it involved too many resources to deal with the computer components. So took a period of time and kept working that, and now here we are in 2016, and we're still working the computer-based components for the logic and for the natural language interpretation. And so, Alex, would you like to say a few words about yourself?
Well, I am a graduate electrical engineer in biomedical engineering and a PhD student in control engineering. But in this context, I would call myself a curious observer or something. I have read a lot about Warfield and all that, so I'm familiar with what you will be talking about. So that's it.
Okay, Mary, would you like to say a few words?
Oh, very briefly. I worked with Battelle Memorial Institute at the Department of Energy down at Hanford site, most recently as a chief systems engineer, but I also ended up working at Boeing, helping them create their production systems management team spanning what had previous to that time been pretty explicit um, pieces of organization that were not speaking terribly well to each other, which I think is probably quite typical. Because of my work with Battelle Memorial Institute, became familiar with John Warfield's work and ended up spending time with him at a workshop in Mexico, then back here in the United States, and conversing with him a fair amount of time. So that's my brief background in that. It's good to have you all here.
All right. Thanks, Mary. Okay, I think what I'll do now is basically just kind of go through the agenda briefly and then talk about some of the components, what we've done recently, and kind of maybe talk a little bit about where the group would like to go in the future. What we have for our agenda, of course, is to discuss the current state of systems development. So we've been working on some software web applications. We've done a strict order type of application where we're using our standard example, which is a NORTHA for ordering cities. Just using this as a basic example of natural language relationship converted to a mathematical relation, and talked about the contextual types of aspects of the context that actually impact that mathematical relationship. We had a strict order, and we had a total order. Also evaluated the concept of a partial order and the complexity that was associated with a partial order implementation, and decided that we would not implement partial orders because they have too much uncertainty in them. So basically there's two sets of software out there right now that are in the web-based type of JavaScript application that demonstrate these ideas. We also went through and verified the mathematics that Warfield produced in his monographs in Battelle using the University of Washington SAGE math tool. So we've done a bit of background work in this in about the last 2 to 3 years. I'm going to switch the screen now and go to our read ahead document and just kind of put this to demonstrate a little bit more context, provide a little more context to what we're doing. And so now let's go ahead and see if I can do that, get a screen share here. And here's the one I want to share right here. Okay, share this one. So basically what this is our structural modeling components that we developed. There's 3 components. Warfield did identified the first 2. He identified the basic structural models over here, the interpretive structural models, and just said basically you needed to put those in proper correspondence. Mary and I developed the 3rd component, the structural integration modeling, to represent the activities that are associated with placing the basic structural models in proper correspondence with the interpretive structural model. We found that when we were doing our preliminary research that this was an area that had a lot of uncertainty and a lot of confusion associated with it. So we decided it needed to be organized and put into a structured format. What happens here is you have the mathematics and the basic structural models, which really is formal. It's a formal logic and matrix theory of graphs that's really used to create outcomes and do types of reasoning that human beings find difficult to do naturally in their head. So this is a type of area where we can use formal models. Interpretive structural modeling is essentially where you engage business, systems, complex systems of all kinds, processes and so forth. These are the day-to-day type of activities that a manager or a designer or an implementer of a large system or operator of a large system, they're involved in it all the time, every day. And it's the domain of natural language and natural language relationships, and the complexity associated with these types of activities really overwhelms people. So the primary goal is to use mathematics implemented by computers to help eliminate the complexity associated with day-to-day complex activities. When Mary and I went through and looked at a lot of the material that was available, especially Warfield's work and some work by others, we found that there was some confusion about the mathematical hierarchy and the mathematical theories and the implementations that we found. So we went through and started working those and developing those in a manner. Good morning, Kevin.
Morning. Sorry I'm late. I had a little trouble.
It's okay. It's all right. Glad to see you here. So as we walk through these particular concepts and ideas, we found that there were natural language and implementation issues and interpretation issues that needed to be highlighted and discussed. So within the structural integration modeling component here, I think one of the goals of the group is to create a set of logical patterns that are commonly accepted between the mathematics and the natural language. So what are these patterns? What do they look like? Come up with simple examples and how they're basically implemented. And of course, we developed the augmented model exchange isomorphism and the abstract relation type to actually package this information and present it in a way that could now be packaged and used as a pattern or packaged and used as a standard type of process. So that's kind of where I think essentially the program or the process or activities are right now. The second web application that we're working on right now is an adaptive total strict partial order, which is kind of a combination of mathematical terms, and we needed to have this adaptive part because when you go into a situation in real life, you go into a real situation, real complex situation, you really don't know what you're going to run into. You don't know what kind of ordering you're going to have, or you don't know if you're going to have a mixed type. So you need to have an approach that's adaptable. And so as you get a little bit of information, you go in with an adaptable system, you do some recon, you figure out things, you adapt, you change your model, you tweak things a little bit, and then you move forward. So what the current software application is at this adaptive part. And that's really rather interesting, to me anyway. So are there any questions so far? Okay. What I'm going to do now is go ahead and good morning.
Good morning.
How's it going, Janet?
Okay, morning. Good that I finally was able to join.
It can be, yeah, it's okay.
I don't know why Michael and I both tried about 7 times. It finally went on his machine. I don't know what was going on. Just kept getting error messages.
You're persistent. That's a persistent test. Glad you were able to get hooked up.
Yep. Okay.
So we've just been going over the kind of the project, the state of the project, and what we've been doing. We're talking a little bit about the web applications that we've done in the past and the mathematics that we validated using the computer-based system from the University of Washington. And then we're talking about the adaptive total strict partial order, which is our current software application. And then I'm going to bring up the hierarchy of mathematical theories, which I think is very interesting and related directly to what we're doing. As soon as I can figure out, okay, there we go. Now we'll see if I can share it. Here we go. Share this. So this was a chart that was prepared by John Soa, and he presented it at an ontology summit, where the focus of the ontology summit was the integration of artificial intelligence applications and computer-based logic systems. And he pointed to this heterogeneous tool set, which essentially is used to integrate these logical systems. And this area, specifically right now, is in theoretical computer science, and a subsection of theoretical computer science then is integration of logic. And so they have these tool sets that allows them to integrate logical systems that have been built on different types of logic. This hierarchy of mathematical theories, one of the things that intrigued me about it was actually just the type of relations. And when we approach a system, we say a system is a relationship mapped over a set of objects. Here we have all these mathematical relations. And we have different types. And I was wondering how the strict order, the strict total order, and the total order that are on this chart really relate back to what we're doing in the software and the analysis that we're doing, because we are doing an adaptive strict total order. And what I found when I asked some questions about this chart, what I found was that this arrow, starting at the top here, you start at the top with relations and all the arrows flow down. The idea in this chart was that the relation has the minimum number of axioms in it. So the smallest number of axioms or logical axioms associated with these concepts is at the relation. Then as you follow the arrows and go down the chart, there are more and more axioms associated with these ovals as you go down the chart. So that for a mathematical, for a computer interpretation or computer logic, then it was going to take more axioms to implement a rich total order down here at the bottom than it would be a plain relation at the top. And so that kind of makes sense from a mathematical, logical interpretation piece. And the kind of the way I thought about it was in our augmented model exchange isomorphism, what we do is we map our logic across logical properties. And we have 27 buckets of those logical properties, 27 categories put together. And those allow us to be very specific or more specific about a natural language relationship. The natural language relationship that we just use to demonstrate the augmented model exchange isomorphism is connected to. And connected to is a very non-specific type of relationship. And it applies in every one of those 27 categories or buckets. And so one of the advantages and one of the uses of the augmented model exchange isomorphism is to actually detail precisely more information about a natural language relationship. And so in that way, it becomes more specific using the augmented model exchange isomorphism. In this hierarchy of mathematical theories, as you go down the chart, you become more specific, so that an asymmetric relation is a more specific type of relation than a relation. And a strict order is more specific than an asymmetric, and a strict total order is more specific than a total order. So in that way, they're similar. What we're doing is we're becoming more and more specific and adding attributes, characteristics to these relations, in this case for the mathematical theories, or in the relationships in the terms of the MEI, to hone in more precisely on what our concepts mean. So, any questions on that? Okay. So, that's kind of the connection there between the mathematical theories and the relationships. And I think that the most important part is that there's the recognition that there are other groups of people that are working kind of in the same area, kind of on the same problems, but they're focused in a different area. So the theory of hierarchy, you see the hierarchy of mathematical theories, that is really over in the basic structural modeling component of what we would think about in the structural modeling. So let's go back and look at that. If I can come up with a screen here again. Here we go. So let's see if I can share this. All right. So the basic structural modeling, so this hierarchy of mathematical theories is over here. And that's the work that's being done through the ontology groups and the integration between different logic-based computer systems is really going to help, I believe, in providing some context for the interpretive structural modeling mapping back to whatever system you really want to use to support it in the computing area. And that, of course, is the domain of the structured integration modeling. So what type of problem, what type of real-world natural language problem is mapped to what type of mathematics and what type of theory in that area. So that's just an indication that there's a lot of work going on in this area, a lot of interest, and maybe as the software and our processes are more well developed, we'll find stronger connections there. So are there any comments, questions, ideas?
Joe.
Yes.
On the previous slide,
Mm-hmm.
Notice that partial order is defined as inheriting anti-symmetric relation.
Let me go back to that one. Let me pull it back up. Okay, right here. Okay, so you say the anti-symmetric, right?
Yeah, but I think there's a lot of literature that defines the partial order as asymmetric, and I'm wondering if that's simply inconsistencies or people just confusing the terms.
Right. Okay, so yes, this, first of all, what I have found and what Mary and I have found in our research across the literature is the anti-symmetric relation appears to cause the most confusion, and the absolute most confusion. And the anti-symmetric component, anti-symmetric relation, mathematical relation, is the correlation in a partial order. The reason for the confusion, I think, is twofold. The first reason is that the anti-symmetric relation contains both an asymmetric relation and a symmetric relation depending upon the context. So there's uncertainty associated with a partial order. You go in, if this, then that, right? You don't find that in any other of your logical relations. And further, the anti-symmetric relation does not allow flexibility in the reflexive logical property. It only allows flexibility in the symmetric logical property. And it was this strict adherence to the anti-symmetric or partial order implementation that doesn't allow a irreflexive type of logical property that generated much of the obvious concern with people who were doing structural modeling, mapping it back to the mathematics, and then taking their mathematics and putting their mathematics into natural language. Very few people did that. A few people did, and the classical example is Donald Stewart's work in the design structure matrix, where he did all this mathematics, and then he said, by definition, events precede themselves. Well, that's just, that's nonsense. But because he was using a partial order that had the anti-symmetric relation, the anti-symmetric relation does not allow an irreflexive type of property. So in our work, we don't use the anti-symmetric relation for a couple of reasons. First reason is the uncertainty. We reduce uncertainty by eliminating the anti-symmetric relation, and when you reduce uncertainty, you reduce complexity. And then when we look at that part, we say, okay, if we really want to be able to take natural language understanding and map it to mathematics, we have to have something kind of like an anti-symmetric relation that we can kind of like use with a partial order, but allows us to say, oh, no, we have a set of events here in the timeline, and the events don't precede themselves. So we really want to have the order associated with the asymmetric component, and we want to have the irreflexivity associated with the reflexive logical component. And the partial order just doesn't allow you to do that. And as we went back, and I think that's one of the primary issues with the self-interaction matrix that Sage came up with, because he maps both asymmetric and symmetric relations on the same chart, and everything gets mixed up. Is that kind of...
I think there's three or four levels of confusion in the literature.
Yeah.
And I started outlining the paper that we talked about doing as a systematic review.
Right.
And so one of the first things to figure out is, why are we doing this? And I think one of the reasons is right here. If you look at applications of interpretive structural modeling, for the ones that do delineate what the logical properties of the relationship they're doing, they lift it from one or two of Warfield's publications, but they don't necessarily know what it means.
Exactly.
And then they talk about it, and one of the most basic things that I see is they map their relationship to the English without really knowing what the underlying logical property is, and they just ignore it. But the math is they're typically using math done by somebody else or software done by someone else, and they do relationships verbally that haven't been mapped to the logic that's in the software. But because the software is already there running, it just goes, and it kind of exists in two different planes. You know what I mean? Like if you
I know it. I think I understand exactly what you mean. And when you were talking about doing the review for a paper, basically, well, why are we doing this review? Then you said, okay, this confusion that's associated with these mathematical concepts and the translation from mathematical relation to a natural language relation, that translation has been just basically bent, twisted, and contorted every way that you can think of. And so to be able to talk about that contortion and what does that mean in a little more precision, Mary and I developed a couple of tools. One is the augmented model exchange isomorphism, which maps the categories of the logic, and then the abstract relation type, which is used to collect the information about a specific relationship and how that specific natural language relationship is mapped directly, specifically to the mathematics. And so that's why we developed those tools, to do that. And yes, I agree with you 100% on that it's very obtuse in some cases, and it just doesn't make much sense.
Yeah, so we need, I mean, you have the tools that you have are helpful for clearly defining what we're talking about when we talk about structural modeling. What we need is kind of a field handbook for identifying fallacies.
Right. So, okay, yeah, I think that there's a, let's see how to do this. Let's think about, let's use an analogy of someone who's going out and exploring the jungle looking for new plants or something, right? So we have categories, and we have some type of science and some type of topology and categorization that's there, but we know they're missing parts, right? And so if we're going to start to catalog and categorize how the logic terms fit together, there's a couple of issues. One is how the logic terms fit together in natural language, and the other one is how the logic and logic terms fit together in the computer science component, right? And in this discussion today is the first time that we've actually brought the computer science side in terms that are really fairly close to what we've been talking about in the natural language side. And the hope, Mary and I, the goal, the design goal for the abstract relation type and the design goal for the AMEI was to present a format to collect this information and to develop patterns. And those types of patterns, I think, is what I hear you saying is the field guide, right? Because, but not just saying what is false, but saying like what is true, and then allows people to document their experience, and also allows people to go back and look at the literature and try to pull standard patterns out that have been documented in the literature. You think that would help? Well, hopefully it will, and making some progress on these particular tool sets and going forward. The
Joe?
Yes.
Yeah, I think there are several layers of things. Maybe before one gets to the level of what you just described, or even the logical fallacies level. One would be just integrating this diagram with your 27 types, so that the diagram is more clearly laid out the way your types are. Maybe we need a few steps of being able to take people through the relation types, and because of the difference in the presentation here and your presentation, it's easier for one's eyes to cross looking at all these labels.
Nicely said. Yes, it is a little busy.
Yeah, so I think that would be a stepping stone. It's rather dry, but for someone who could make their way through it, they would grasp why these things are fundamentally different from one another, asymmetric, antisymmetric, that kind of thing. That they can't just gloss over the distinctions. So I guess that would be wouldn't be a field guide, but it would be a field. It would be a zoo of types, and then one can move on to a field guide at some point. Anyway, I also wanted to say that Kevin's history that he presented at the IW was really good, and that helps provide some context for understanding. It's orthogonal to what we're talking about, but it also helps provide some understanding of the what is going on in this kind of modeling, mapping to the mathematics and back again.
Joe, in your chart of the 27 combinations, are they? I don't recall. Are they labeled with the names that are in this diagram, the hierarchy diagram?
Well, actually, they're not, and the reason they're not is because each one of these names on this chart can have different logical properties associated with it, depending upon which branch of science and literature you're reading. And so out of theoretical computer science, where this is coming from, might be a little bit different than formal logical mathematics. And what I have found is I have found different logical property groups associated with the same name tag for the names that are on this chart. And so the reason that our fundamental augmented model exchange isomorphism does not have these name tags, because I couldn't find a set of information that was consistent. But the 27 groups are consistent. They are properties. You can, like, go look for a big tree with green leaves and broad leaf limbs and things like that. So
we need a cross-reference between them, because when you get to, like, most of the publications on interpretive structural modeling aren't research about interpretive structural modeling. They're applications of it. And when you get to that level, it's really loose. That's what I mean by the field guide. Before you, I think we need, like the world according to SOA cross-reference to the 27, and the world according to Warfield cross-reference to the 27, and so forth.
Good. Yeah, I think that's a great start. I do have some other material up on the System Concepts website, where we started, I think about 6 months ago or so. We put up some charts that kind of started to do that. And it sounds like an interesting mapping activity for the group to become involved in, because it's, I've started doing some of that, and I do have some, of course, we have the information that from Warfield's books. I think there's 30 or 40 relationships there. So I think that there's an opportunity to do that. Now that we have the AMEI, we can take those buckets and we can start taking these relationships and putting them in there.
Yeah. Then, and then to bridge over to the interpretive structural modeling, then there's additional relational properties about reading the structures beyond the ones that are listed here. For example, when people model influence relationships,
right,
it's often cited as being a partial order.
Right.
Whether the structure they're reading, like suppose you have a node in your diagram that is influenced by A and B.
Mm-hmm.
A and B both influence C, right?
Right.
So the interpretation of that is all over the map. Some people say, they'll in their work they'll treat it as A and B are necessary for the completion of C.
Yes.
Other people say no, it just means that if A exists and B exists, it's helpful towards C, but there may be other things that are not on the map that are necessary for C. And then other people interpret it as A and B are sufficient causes of C, right? So influence is one of the more complicated linguistic properties that get mapped onto this, but it's even to get into the causation things, you need necessary and sufficient as additional properties that are kind of like logic gates, whether it's a logical and or a logical or on either side of the node coming. So like things that would be sufficient, it would be a logical and. A and B are both necessary to the completion of C, versus an OR gate coming in. And so where A or B is sufficient to cause it, but you don't need both. Just A or B. So there's exclusive ORs, there's inclusive ORs. So there's a whole nother, beyond these properties. This chart is primarily going over the reflexive, symmetric, and transitive combinations, but there's other relational properties when you get into particular things like influence. So this is like the first level.
Oh, Kevin, I couldn't agree with you more. I think that there's a lot of things that are going on, and I've thought a little bit about the areas that you're talking about, and I think we, as a group, we really need to think about where is the boundary between structural modeling. Right? I'm just creating a structure, and then the boundary between the structural modeling and the behavioral modeling. Okay, so I can have a structure that behaves in different ways depending upon the assignment of the logical properties to the components. And so that's kind of one of the ideas that I've been thinking about is, okay, where do we do that? Where do we start in structural modeling? Where does structural modeling stop? And where does behavioral modeling start? And because you have to have structure to have behavior, right? And those are some key things that I'd like to have the group think about, and to get some discussion going on that. Because what I hear you talking about with the causation and the logical OR gates and AND gates and so forth, that to me is getting a little bit more into behavior. We're going a little bit away from just a graph theory. If you think of the structure of what we're doing, creating a structure which basically is a graph, and then moving a little bit forward, it's almost like some of the things you're talking about are almost like an automata machine. It's a graph that actually executes behavior. And I think we need to start making some distinctions there, or we'll start getting things confused. But I agree that we need to do those things.
I think that Warfield dealt with only 2 nodes on this whole diagram.
Okay.
Total orders in the software he implemented. He had total orders, which he called priority structures.
Right.
Which is an unfortunate name because it implies it's only used for doing preference modeling.
Right.
But it meant a total order, and then partial orders.
Right.
But I'm pretty sure that when he defined partial orders, he didn't define it as. I mean, he may have done it different ways in different places, but I don't think he used the term antisymmetric. This is one of the confusions.
Right.
I think he called a partial order things that were asymmetric, irreflexive, and transitive.
Okay, so I think you hit on a very key point of Warfield's work as we start mapping it in generally to what we see today in logic. And if we go back to the binary matrix paper, and you talk about what is it, condensation, where you take a graph that has both a symmetric structure components and asymmetric structure components, and you apply those processes, and then you generate a new graph that is only asymmetric. In that particular case, and those mechanisms then translate. There you're going from you're translating the graph, the same structure, the same system, but you're putting it into different structural views. And you don't see that much today. And another interesting thing about the mathematics that Warfield did was the way that he described a matrix, and then the way that he used the mathematics in that matrix, it appears to me what was going on, that he was actually doing a type of what you call binary or Boolean inference, which you don't see today at all, hardly ever. And he does that in a type of mathematics that was, basically lost, I think, to most people today. And there's a process that you go through to do that has very little connection to the mathematics today because of certain ideas about field theory in mathematics and certain ideas about group theory in mathematics, and the fundamental disconnect in Boolean types of mathematics to those two concepts. So without going too deeply, that's kind of a disconnect for sure from what Warfield did to what we see today. And what I've been trying to do, and what I think I've demonstrated, is that we can address some of those issues and use the modern mathematical tools like the SAGE math tool from the University of Washington to reproduce and do the same types of things if we understand these specific anomalies in the mathematics and the procedures that Warfield was doing and why they're not implemented today in most of the mathematics tools we see. So there's some of that. Does that make sense?
Yeah, that makes sense.
So okay, so we've got about 8 minutes left today.
Joe, another quick question. The left total relation and right unique relation bubbles.
Right. Yes.
What was the description of those? They apply to everything. Why are they not connected?
Right. So that's an excellent question, Janet. I asked that question to the person that created the chart, and he referred me to the website that's listed on the bottom of the chart and said, this is the information I got from that website. So I went to that website and I kind of scanned through some of the papers, and I scanned through a tremendous amount of the information there, and I found a significant percentage of mapping of terms in the papers and with the terms that are on this chart. However, I did not find why those two weren't connected. So I didn't get an answer for that. And it's something that would be, as time allows and as we start sorting this out, it would be interesting to see what we come up with on that. But I don't know why.
But which two are not connected?
The one here at the top, the left total relation right here, and the right unique relation. See those?
Yeah.
They're not. Yeah, they're just disconnected. So, but this is. I think that this is really a good idea to try to map these to the 27 buckets, and then we'll start. Starting to make a relationship there, because I believe that each one of these relations on this chart map to existing sets of logical computation tools that have ontologies built with them that allow you to deal with automatically or in a computerized fashion with large amounts of computerized digital data. So it's kind of a doorway. It's kind of a Rosetta Stone, if we can start mapping these a little bit. So for next June, so Kevin, you say you're working on the outline of that paper? Is that what you said?
Yeah, what I'm suggesting is that we do it in the form of a systematic review following. The idea of the systematic review came out of medical science, where they'll look at all the publications in a particular technique or treatment and try to sum up a meta-analysis of what's going on, but also to instill some type of standardization and quality assessment of things. So in the medical field, systematic reviews have become pretty well developed, and there's people that have kind of mapped what that means into the realm of information sciences.
Mm-hmm.
Because, for example, you typically never get to review a randomly controlled trial in information systems.
Right.
So there's some adjustments in interpretation of the systematic review for outside medicine, but one of the first things to do when you do the systematic review is to clearly identify the purpose of why we're doing this. And I've been just reflecting on that. I think that'd be a good thing to correspond about, or for everybody to think about. I mean, to me, the most basic aspects of this is that this is a technique. I'd like to write kind of the life of an algorithm here.
All right.
Because it got born and then very quickly proliferated in re-implementations all over the place.
Right.
None of them became dominant.
Right.
And it also emerged prior to back-end systems that they could drive.
Right.
It's a natural to use ISM to drive the creation of systems dynamics models.
Sure.
But when they were creating it, there weren't packages that had a standard interface that you could just plug in. There's no API. There was hardly any systems dynamics packages at the time, and there certainly wasn't the idea of an API that you could just write the interface and take the structure and drive it. And now there's a huge number of packages out there. Not a lot have standard APIs for them, but there's some. And so people would go a step further, and they write their own backend, and typically for a very constrained situation, or just very constrained type of property. And then people implemented them in different ways. So to me, one of the primary purposes of doing this is that bigger picture of a consolidation to some common standard, to build some economies of scale of having multiple a larger number of people using the same package.
Sounds great.
That's how software gets higher quality, is you have a larger number of eyes looking at it and banging on it. And right now, it's so fragmented. There's a few people each using their particular implementations, and then a lot of the publications, people aren't even using software to do interpretive structural modeling. They're just hand filling out matrices, and like a lot of the stuff that comes out of India, you hardly ever see any structure that has more than 10 elements.
Yeah. There are. And there appear to be some issues there for sure. And what I'll do is I'll take a cut at starting to map this hierarchy of theories over to the MEI, see if I can come up with some reasonable things. I'll put that out in a read-ahead draft in a week or so. Anybody that's interested, be sure and comment on that and see if we can get a little bit more of a team development on that. And we'll look forward for the next June meeting. Are there any final statements or comments anybody would like to make?
I'll send out this first piece on developing a systematic review, which is the discussion of purpose, because for methodological reasons, it's important that you get that stated before you do the review.
Great, sounds good. Anyone else? Well, Peter, it was nice having you join us today. Hope you join us again in the future. Janet?
Thank you.
Mike, Alexander? We'll try it again next month. Thank you very much.
Thank you.